Hi, I'm Subhashni, and today I'm here to talk to you about the second type of linear regression that we can do, which is on summarized data. This data would often be a time series data. So let's get on. I do hope you like and subscribe to the channel. If you might remember, just to refresh, the first type of linear regression that we had seen was on small data where we needed to create a bigger sample. The case study that we had done was the employee satisfaction score. And there we had seen the concept of correlation. We had also understood that this same project can be done in Excel as well as in Python. Today, we are here to talk about the second type of linear regression, that we will conduct across summarized data. And the case study we are going to consider is the bike usage prediction case study. Do we all understand what is time series? It is a sequence of data points that occur in successive order over some period of time. And these are the most common examples of time series. The first one you can see is the sales over a period of time. Then you have the price changes over periods of time. For international iron ore and aluminium. And then you have the stock market predictions, where the price of the stock goes up and down over periods of time. So these are three very, very common values. And today we are going to look at the bike usage. In front of you is the plot of the count of bikes by period of time. The time period is every day, the total number of bikes that were used between 2018 and 2020. So let's get started. Like our previous case study, we are going to look at this case study in Colab notebooks. And here, again, like all our previous case studies, we are going to be using the Decova and I process. So let's get started. The first part is, of course, importing pandas as PD. Why is this? If you will remember, you have the option to run all, you know, and ensure that the whole set of codes run. But here, that's not what we want to do. We'll go through the codes in detail. So pandas is the library which looks at data frames and structured data in Python. Hence, it's extremely important to bring in this data because our data is completely structured. It's got definitive rows and columns. From Google, we will import the drive. So we actually will mount the content drive because that's where our data set is there. And then from the content drive, after it's um, attached to the code, we are going to import in the bike sharing by day.csv that we have kept in our Google Drive. So here you go. Now, the first thing to check over here is, of course, how does the data look? And if you see in the data frame head, we can see that we have the instance and the date, the season, year, month, holiday, weekday, working day, the weather situation, whether it was good, bad, or ugly, temperature, and so here you will notice there's a temperature and an a temp. Okay. So what are these? This A temp is actually the maximum temperature. HUM is humidity, wind speed, and then we have two components of the total number of people who have taken a bike out on each of these days. The C and T is the total count, and this is made of registered, where the people have gone and registered for the bike on the website. So you knew that they will come and pick up the bike. And then you have something called casual, where they have just walked into the stand and picked up the bicycle. If we want to just understand a bit more about the data, Let's look at it. What are the values? This is for our assumption consumption, um, that you know exactly what is the values that we can see in this data. So the lowest count or the average count is 730, and the lowest count, the minimum count you can see is about 22 people, while the maximum count on a day is 8,714. So that's a huge variation, isn't it? There's a huge variation. So let's understand exactly how we spoke about the fact that we are doing it on summarized data, on time series data. So let's exactly see how the data looks. For this, we import in the matplotlib library, and we want to do a simple line chart. What are we mentioning? We are checking the count over periods of time. So when you run this, you get a chart like this, which tells you, and you can see that you know in very close days, matlab days very close to each other, you have such wide swings in the count of people who have picked up a bike, right? So there is some sort of a seasonality, but a lot of it seems to be quite random. Now, one of the things we have done earlier and which you might want to do for this case study is to look at the SweetWiz report, which is the exploratory data analysis report. So go ahead and do it. You've already done it in the previous case study. I know you know how to do it. Let's get on to the part that we had not really covered. So on looking at the info around this data, we find that nearly every column or variable in this data is numeric. There's just one day, which is a date time function. So let's actually see how the data looks again, especially when we are looking at the box plot for count, because that's our y variable and we really want to know, do we have outliers in this? Correct? We would want to check for outliers in the y variable. Here you go. We had spoken already from something as low as 22 values up till 8,600 plus values. You have a whole range in which the data exists. How many bikes were taken in a day? And we can see that the mean or median part to it is around 4,000 plus, right? 4,500 type of thing. And a majority of the values are in the 3,000 to 6,000 range. This is the most common range in which people pick up a bike. This image shows no particular outliers. So what we want to do is to calculate the outliers using what is called the interquartile range. So, 25%, 50%, 75%, and of course you have the 0% and 100% on the left and the right side. Can we look at the calculation and understand if there are any outliers in this data? Okay. So what do? We find out the 25% and the 75% values, quartiles, and then calculate the interquartile range. Now, what is the lower bound or the minimum which will qualify? It will be the Q1 minus 1.5 into the interquartile range, while the upper boundary, which is the maximum, which will qualify as not being an outlier, it will be Q3 plus 1.5 into the interquartile range. And then what we really want to do is to understand that are we busting this interquartile range and does anything qualify for an outlier? So then the system should print that out for us. Let's see. So the calculations you can see over here, 25th percentile is 3,169. The 75th percentile is 5,966. The interquartile range is 2,796. And the number of outliers is 0. So what the system is saying, given the distribution, there are no outliers in our y variable. Very good. Now, what is the the um, derived variable we want to do. So what I really wanted to do is to create something called the unregistered base, because I didn't know what casual was. So I thought, let me check, can I run something called unregistered, which is the total count minus the registered values. So yes, I've done that here. Unregistered is equal to df count minus df registered. And if we run this, we can see that a new variable is created over here called unregistered. Okay. Now, what we want to do is we want to drop casual, registered, and unregistered before we start with anything. Why is that? Because casual, registered, and unregistered, and year, what we don't really want them in our model. What is registered and unregistered today is giving together gives us count. Casual, we will realize, is actually the same as unregistered. Okay, so all of these we want to remove before we run the correlation. Okay, these all go into the creation of the y variable, casual, registered, and unregistered. And the year function doesn't matter because we cannot repeat those years again in the future, right? Those years will never be repeated. So then what we want to do is to run the correlation. You will have the code already for the correlation from the earlier data. And one of the things we want to do is to remove anything which is non-numerical, right? We want to not have non-numerical data in the correlation because then, of course, it will not run. So let's know beforehand where exactly are the non-numeric. So here you can see that date a day column is the one which is non-numeric. We have already seen this. Everything else is numeric. And with this, what we do is we create the correlation matrix, which is the data frame of the numeric columns and running a correlation of each of the values with each other. Here is the outcome of the correlation matrix. Some places there's a positive correlation. Some places you will see a negative correlation. Great. Okay. So what's my y variable? My y variable is the count. I really want to be able to predict the count of bikes that will be used given the weather condition. And with this, what we want to do is that the correlation has run. Can we visually understand what it looks like and run a heat map for ourselves? So let's go ahead and run a heat map for ourselves. Again, as I mentioned to you, all these codes are there in our earlier case study also. So this is not the first time that we are doing it. This is the correlation matrix that gets created, printed out. Okay. This is the correlation heat map where we can see the relationship of every value with the every value. Okay. Now, obviously, it's not so easy. The number of columns is quite big. So we really find it a bit difficult to figure out which are the values which are most correlated to the y variable, which is the count. So what we do is we try to create through the system itself, we want to rank out the correlation of each of the variables with the count or the y variable. To do that, what we do is we calculate the correlation only with count and then run a ranking code. So we say rank in ascending is equal to false. Okay. So the maximum value has to be the first one, that is descending is equal to true, and display the values. So here you go, that the most important value seems to be the maximum temperature. The instance actually is just a counting of it like a roll number. So I think that we don't need to consider. We can as well drop it. We should have dropped it ahead, and maybe you can do it when you start writing the code. The temperature, season, the weather situation, the month in which we are considering, wind speed, humidity, holiday, weekday, and working day. Now you can see that actually the fact that it's a holiday, a weekday, or a working day seems to be very low correlated, 0.06. Okay. Humidity is also pretty low correlation to the count of bicycles that are used, right? So this is an output which makes it easier for us to interpret things. Okay. Um, Now, what we want to do is we want to drop holiday, weekday, working day, and year. Year we have already dropped actually. The date exactly. We want to remove it. Okay. So just the values which we haven't dropped, we're dropping it out. Okay. And we can see that now we have a much smaller data frame after doing the drop statement. We have kept what we consider most important. And then what we want to do is define the target variable as count, okay, and create the X data set and the Y data set. So here you go. You're creating an X data set and the Y data set. From sklearn, we want to import in the train test um, split function and split the data into training and testing data. Test data is 0.2, that is 20% of the size, and training data will be 80% of the size. So let's go ahead and do that. Okay. And from sklearn itself, we will import the linear regression and also import the different functions required to calculate if our linear regression is good or bad. Okay. Again, I hope you will remember that we have done exactly the similar thing in the earlier case study, except, so what is the thing? The code itself is the same. What really matters is the fact that the data set is different and the interpretation of the outcome could be a bit different. So let's look at the outcomes which have come. The mean square error is showing some 8 million type of figure. The R square is showing 0.77. That is 77% of the time the system will correctly identify a value. And then the testing data is showing an R square of 0.81. So it seems to be more efficient. The model, when tested, was more efficient than on the training data set. So great, let's go ahead. R square of training data is below 8, but the testing shows 0.8, which is good. And what we want to do is to display the coefficient and know exactly what is the equation that we're talking about. Let's print out the regression equation. So we look at the coefficients which are created, ask the system to create the equation and show it to us so that we don't have to manually sit and do the equation. And here you can see the equation. Right? So it's showing count is equal to 1564 plus 5.43 into instant plus 544.9 into season. Now we should rerun it without instant because instant is just a sequencing of the values. Okay, so I'll just write it here and this will be your assignment to rerun it after dropping instance. Okay, so let's look at the outcome visually. What are we saying? So let's see how, if we were to create a prediction column in the data set, what will it predict? So you can see it is predicting 18, 1801, 1587 and such values, saying that on this particular date, this is what is going to be the values. Okay. Now, one is looking at the R square and through numbers understanding that how good or bad is the model. One is doing it with a graph, and I'm sure that you would also enjoy looking at a graph rather than looking at the numbers. So this is the red lines is the predicted count and the blue lines are the actual count. So it's giving you an idea how well is your values getting predicted. Okay. Of course, one of the things I can do is to actually export out the file with the prediction so that I can store it for later. And what I would want to do is also that from sklearn, I might want to just do a comparison of all the metrics that we have done for test and train so that we have them all in one place. Okay. Now, an R square of 0.8 is considered good, while so here what we find is that 81.60% of the variance in the target variable is explained by this model, which is really great. But a question could come, how will this process really work? Because here we have the temperature, humidity, etc. for every day, right? And the system model is able to do it. Now, what will happen really? So here what we are saying is that we would connect our data to a site, a weather site, which does a prediction of the weather with temperature, humidity, etc. for the next few years and months and days, right? Of course, the year predictions are least accurate, and the day wise predictions become more accurate. They adjust as different storms and different movements in the system happen. So if how would we really do it? We would actually get a weather report for the next few days. Like here I have created one, looking at the mean values and the standard deviation, created one which has instant date, day, season, month, weather situation, temperature, max temperature, etc. And then what we want to do is to run that through the model. We will run it through the model, and the model will tell us that for the next week, every day of that week, given the weather that is expected, how many units of people can be expected. Okay, so here you go, you can actually see that it will tell you that for each date, given the temperature, what is the counts that you can expect. Okay. And when you print it out, you can see that this is the prediction for the next day, a few days, I think 180 days, right? Till 2025, there's a prediction out here. Okay. So I hope that gives you some sense of how these models work. And as I mentioned to you, remove the instant and rerun this model as your self work. And I look forward to seeing you again for the next type of linear regression models. So for the next 180 days, this is 1.5 years, given the temperatures which are loaded and the humidity, etc., loaded into a website which has weather prediction. These are the values that the company can expect. With this, I will close this session, and I look forward to seeing you really soon.